Hello and welcome to this explainer. Okay, I am so excited to take you on a journey today into the literal building blocks of our modern world. Look, chemistry is, well, it's completely unavoidable, right? It's the reason we have life-saving medicines, super durable materials, and all the food we eat. But traditionally, it's come with a massive environmental hangover. For the longest time, industrial progress just meant accepting this huge, heavy toll on our planet. But today, we're going to dive into a totally revolutionary concept that is changing all of that. It really all boils down to this one essential question. Can we create the chemicals we rely on without that toxic hangover? Basically, can we have our cake and eat it too? Can we manufacture the millions of products that our global society relies on every single day, but without generating the staggering amounts of toxic waste and emissions that, threaten our ecosystems? For a really long time, the answer was a pretty reluctant no. But as we know, science is incredibly adaptable, and a massive paradigm shift was right around the corner. Enter green chemistry. This popped up prominently in the 1990s, championed by visionary scientists like Paul Anastas and John Warner. And honestly, this isn't just some new technique, it's an entirely new philosophy. So green chemistry is defined as the design of chemical products and processes that reduce or completely eliminate the use and generation of hazardous substances. Instead of figuring out how to clean up a giant mess, the goal here is to just never make the mess in the first place. Okay, let's dive into this. Here is our roadmap for the explainer today. We'll start with 1, the chemical problem. Then 2, enter green chemistry. 3, the 12 principles. 4, measuring efficiency. 5, everyday green chemistry. And finally, 6, a sustainable future. Let's kick things off with Section 1, the chemical problem, traditional chemistry's hangover. For over a century, traditional manufacturing has operated kind of like a really messy cook in a kitchen. They get the meal made, sure, but the collateral damage, absolutely huge. We are talking about severe byproducts here. Highly toxic wastes that literally poison waterways, harmful emissions just pumping right into the atmosphere, synthetic products like certain plastics that are completely non-biodegradable, and massive, massive energy wastage just to force these chemical reactions to happen. The environmental and economic toll of this reactive, old-school way of making things is, well, it's just simply unsustainable. Which brings us to Section 2. Enter green chemistry, a proactive solution.
Now, what's really interesting here is the sharp contrast between environmental chemistry and green chemistry. They honestly get confused all the time, but they are very, very different. Environmental chemistry is fundamentally reactive, right? It studies pollution after it's already in the river, it monitors the contaminants. But green chemistry, it completely flips the script. It is entirely proactive. It focuses on preventing pollution at the molecular level by designing safer chemicals right from the ground up. It's exactly the difference between treating a disease and preventing it from ever occurring in the first place.
So, how do chemists actually achieve this? That brings us to Section 3, the 12 principles, the rules of the green game.
Anastas and Warner actually laid out 12 foundational principles, and we've grouped them here into 3 easily digestible themes: waste, safety, and efficiency. Under waste, the golden rule is prevention. You want to use renewable, plant-based feedstocks instead of finite petroleum. Now, for safety, it's all about designing less hazardous synthesis routes and actively preventing accidents, minimizing explosion or fire risks. And then for efficiency, it just means doing a whole lot more with less, using catalysts to speed up reactions, lowering energy consumption by running things at room temperature, and using real-time analysis so you can stop pollution the actual second it starts. And this brilliantly illustrates one of the most absolutely crucial safety principles, swapping out solvents. Historically, industries used incredibly harmful solvents like benzene or chloroform just to dissolve materials. But today, green chemistry pushes for some truly brilliant alternatives. We can often just use water. It's cheap, it's completely non-toxic. Or take supercritical CO2, which is carbon dioxide pressurized into a fluid state. It's entirely recyclable and, get this, it's actually used right now to decaffeinate your coffee. Then you also have ionic liquids, which are essentially liquid salts that don't evaporate into the air and can be reused over and over again. Moving right along to Section 4, measuring efficiency, the math behind the magic. You see, green chemistry isn't just about good intentions. It is a rigorous, quantifiable discipline. One of the absolute most vital metrics here is atom economy.
Basically, this measures the efficiency of a chemical reaction by calculating exactly how much of the reactant's molecular mass actually ends up in the final product. Think of it like baking a cake. If you put in a pound of ingredients, you want a pound of cake, right? If you end up with half a pound of cake and then you throw half a pound of leftover batter in the trash, well, that is terrible atom economy. Mathematically, it's simply the molecular weight of your desired product divided by the molecular weight of all your reactants. Because in chemistry, every single discarded atom is just potential pollution.
100%. That right there is the absolute holy grail of green chemistry. Certain types of chemical processes, like addition reactions and catalytic hydrogenation, they can actually achieve nearly 100% atom economy. Let that sink in. That means every single atom you put into the reaction vessel becomes part of the final product that you want. Zero waste. Absolutely zero molecular garbage left behind. It's incredible. Now, another crucial way industries measure their footprint is something called the E factor. This looks at the mass of waste generated divided by the mass of the final product. Honestly, think of it kind of like a golf score. You want the lowest number possible. A low E factor means you are creating very little waste compared to your useful product, so highly environmentally friendly. But a high E factor, which historically plagued industries like pharmaceuticals, by the way, means you are generating literally mountains of toxic waste just to get a tiny, tiny amount of usable product. Now that we've got the math down, let's bring it into our homes with Section 5, Everyday Green Chemistry, Real-World Impact. You know, you might not even realize it, but you are already benefiting from green chemistry every single day. I mean, just the phase out of lead in petrol was a massive green chemistry victory. It drastically reduced hazardous air pollution and neurological health risks worldwide. Or when you wash your clothes with eco-friendly biodegradable detergents, you're actively preventing water systems from choking on toxic suds. And those water-based paints you use in your living room, they were engineered specifically to replace old oil-based paints, completely removing highly toxic volatile organic compounds, or VOCs, from the air your family breathes. Let's look at a really specific industrial triumph: ibuprofen. It's one of the most common painkillers in the entire world. But originally, its manufacturing process was incredibly wasteful. It had a terrible atom economy that produced massive, massive amounts of toxic byproducts. So, by applying green chemistry principles, scientists completely redesigned the synthesis process. And the new method? It not only drastically reduced waste and improved public safety, but it actually saved the pharmaceutical companies an absolute fortune in hazardous waste disposal costs. It is literally the perfect win-win. We're also using these exact same principles to tackle the global plastic crisis. The polymer industry is finally shifting toward bio-based plastics. So instead of extracting finite petroleum from the ground to make materials that will, outlive us by thousands of years, scientists are engineering plastics derived from plants and agricultural waste. And the best part, following the green principle to design for degradation, these materials are chemically structured so that they break down naturally and completely harmlessly once their useful life is over. All of this brings us to our final stop, Section 6, a sustainable future. So the crucial point here is that green chemistry is not just about fixing our past mistakes. It is quite literally our primary toolkit for survival in the future. As we face down climate change and much stricter environmental regulations, the technologies on the horizon are just breathtaking. We are looking at carbon-neutral manufacturing that doesn't add a single ounce of greenhouse gas to the atmosphere. We're seeing the dawn of green nanotechnology for safer medicines, and even artificial photosynthesis. That's literally borrowing from nature's playbook to create energy and materials using nothing but sunlight, water, and CO2. How cool is that? Which leaves us with this final, really vital thought. Green chemistry proves that industrial progress absolutely doesn't have to cost us the Earth. The science is here, the principles work, and the economic benefits are completely proven. But if the future of our survival relies on fundamentally reinventing the very molecules we use today, well, how quickly can we push past the old ways and completely transform our entire industrial world? The clock is ticking, for sure, but thanks to green chemistry, we finally have the right formula. Thank you so much for joining me on this explainer today. Keep asking those big questions, and I'll catch you next time.